Hey, what's up? It's your old pal, Mr. Cook, and we're going to continue our videos going over the test review for Unit 4. So in the first video I made, we went over methods for determining which type of procedure to use for each of the antiderivatives. So I recommend watching that video first. I'm just going to focus on, implementing some of these methods. So in this video, we're going to be going over integration by parts. So in integration by parts, you have two functions that are multiplying together for the most part. Sometimes like you won't see the function at first, but it's there. Like sometimes dx is one of the functions, for example, because it gives you a constant when you take the antiderivative. Now, in general, like you want to remember the formula for integration by parts. It comes from the product rule. And basically, it looks like this. So integral u dv. So these are two functions that are multiplying together, u and dv. It ends up from the product rule becoming u times v minus integral of v times du. So you need to memorize this pattern for the test, and just in general, it's good to know the integration by parts pattern. When you're in a calculus class. Okay, so with that in mind, we're gonna go through this now. There is some like question about like which function should be the u and which one should be the dv. So I learned from one of our math teachers, Mr. Rupp, that if if you're like the main thing is that you want to focus on the function that's going to be a u. And the most part, like you want to be able to take the derivative of one of the functions that reduces the function down. Okay, so if it goes laterally, like for example, e to the x, if you take the derivative of e to the x, it's just e to the x, or sine of x is cosine. It doesn't really go anywhere. It doesn't reduce the overall antiderivative. It doesn't make it any less challenging, or sorry, it doesn't make it any easier to work on. So there is kind of like an ordered tier by which you want to pick out the u to reduce it to make it easier. And here's how it goes. You just remember a word, liate, L-I-A-T-E. So the L part would be natural logs or logs. And this should make sense because, in a little bit when you do integration by parts, you have to do the derivative of the u part to get to du. You have to do the antiderivative of the dv part to get to v, okay? To fill out all the parts that you need. But the thing is with natural log and log, you only know how to take the derivative of those things. So it only makes sense to just use natural log and log as the u part. Same thing for the next part, inverse trig functions. So if you see an inverse trig function like arcsine, arctangent, that would take priority to be the u as well. A would be algebraic stuff. So that would be like x squared, 3x squared, 5 minus the quantity 5 minus x raised to the third power or something like that. Anything, any function that's just like x, like a polynomial or something like that, liate. So A is the algebra part. T is a trig ratio, so like sine, cosine, tangent, any of those. And then E is exponential, e to the x, e to the 4x, those kind of things. Okay, so just get to know that part, and I'll show you a couple times how to use it and stuff as I'm going through this. All right, so let's start with our first integration by parts problem number 4. So I've got x sine of 2x dx. Let's see. So again, I went through a video telling you how you know it's going to be integration by parts. So let's just go ahead and do the integration by parts on this. So we go through liate. Is there a natural log or a log function? No. In here? No, it looks like it's just sine of 2x and regular old x. And a dx. We can't forget about the dx there. Is there an inverse trig function in there? Like arcsine, arctangent? No. Is there an algebraic expression? Yes, there is. This x right over here. So the idea is this. When I use the algebraic value for u, I need to eventually find du. And what's the derivative of regular old x? It's just dx. So like when I plug the derivative part in over here for this pattern, for the integration by parts pattern, all that's going to be left is just a dx. So it essentially like whittles the function down a little bit. It like reduces it a little bit, makes it easier to integrate. Okay, so that's what I'm going to do. I'm going to use that for my u value. X is going to be u. And that means that my dv is going to be the rest of the stuff. So sine of 2x dx. Okay, so to fill all this stuff out, it looks like I've got the u part already here, but I don't have any of the other things. I need v and I need du. Okay, so I need du, which means it's the derivative of u, and I need v, which is the antiderivative of dv. So the derivative of u, the way that I find that is by taking the derivative of just x, which is dx. Antiderivative of dv, v is going to be equal to the antiderivative of sine of 2x dx. So that's a simple u substitution. Antiderivative of sine is a negative cosine. And then from the chain rule, I'd have to have like that 1/2 out front. Okay, so now I'm going to put together this integration by parts pattern. So this is where I started off, x times the sine of 2x dx. And then I just fill it out. So u times v, and then v to u. So this other teacher that I knew named Dr. Dastu, she taught Calc 3, linear algebra, and differential equations and AP statistics at Desert Vista for a while. She had this like thing that she used to memorize. Well, that she would use to memorize the pattern. Once you have it set up like this, u and du, dv, and v. She says that to understand the integration by parts pattern, the knows. Okay, so it goes u times v, v du. Like it makes a little nose right there. So that's like a way that you can remember it, because u times v is like this part, v du is this part. Makes a little nose. I don't know. I thought it's a cutesy little way of remembering the pattern if you're having trouble doing that. So anyways, I do u times v, so that's going to be x times the other stuff, negative 1/2 cosine of 2x, and then minus v du. So v du is going to be v negative 1/2 cosine of 2x dx. So the idea with integration by parts is that it takes a complicated integral and then it makes it into a simpler integral. And if it's simpler or about the same, you've done a good job. You've like kind of helped yourself out in the long run. Okay, so yeah, this is a much easier antiderivative. In fact, I'm just going to go ahead and multiply some stuff together. The negative times the negative gives me a positive there. And then let's see. Let's go ahead and make this look a little nicer and then do the little antiderivative. So I'll put the x probably over the 2 there, cosine of 2x, so just making this part look a little bit better. And then plus, and then the antiderivative of cosine of 2x is sine of 2x. But then I also gain a 1/2 out front. And I also have this other 1/2, so I got to put that on there too. And then plus my constant. And I can just leave it like that. That's pretty much it. Okay, so that's our first integration by parts. Let's keep going through, find some more. There's another one. Okay, so this is one where we have to do integration by parts twice. So we go through our little Lie pattern. L-I-A-T-E. And, let's put our integration by parts pattern on here too. U dv equals uv times minus v du. Okay, so I've got two distinct functions, x squared and sine of x, and then a dx. So let's go through Lie. L, natural logs of logs. We don't see any of those. I, inverse trig. I don't see any arcsines, arctangents, any of that. A, algebraic. Oh, yep. That's where I've got it. X squared is an algebraic expression. So I'm going to let u equal x squared. That means that dv is going to be the rest of the stuff. So sine of x dx. And then I've got to find the rest of my things. So du and also v. So du is going to be 2x dx. And then antiderivative of just a regular old sine is negative cosine. Okay, and then I make a little nose, u times v, v du. And I write out my pattern. So x squared sine of x dx equals, and then let's see, so u times v, so that's going to be x squared times negative cosine of x dx, or so negative cosine of x, no dx there, sorry, minus integral v du, so negative cosine of x, and then times 2x and a dx. All right, so let's make this look a little bit nicer. So we've got x squared. Let's put the negative out front, and then cosine of x. All right, so that's that part. And then a negative times a negative is a positive, so plus integral. And I'll move the 2x out front. 2x times the cosine of x dx. Well, you know what? What I've just made, this integral right here, this is easier to work with than this one because I don't have that stupid x squared there. But it looks a lot like number 4. See where I have like an x times trig expression. So that means that I'm going to have to do integration by parts again. And this happens every now and then. Sometimes you got to do it twice. The idea, though, is that, the integral is easier. So you're making a step in the right direction. So I just do integration by parts one more time. I do Lie again. No logs, no arc sines, arc tangents. But I do have this algebraic expression. So let u be equal to 2x. And dv is equal to the rest of the stuff. So cosine of x dx. du is equal to 2 dx. And then v is going to be equal to antiderivative of cosine is just sine. Okay, so I write it again. So what do we got here? So I still have that negative x squared cosine of x. That doesn't go away. Plus. And then now I've got uv v du. So u times v is 2x sine of x minus, and then v du is going to be the integral of, let's see here. So v is sine of x. And then du is times 2 dx. All right, I'm just going to move that 2 out to the front there. There we go. And then this is a pretty easy antiderivative to take, right? It's just sine. So let's see what this ends up being. So negative x squared cosine of x plus 2x sine of x. And then I've got a minus, and then let's see here. Antiderivative of sine is going to be negative cosine. So that means that this turns into a positive 2 cosine of x, and then plus my constant. Oh, did I forget to write plus constant on the last one? No, I got it. Okay, I just want to make sure. Yeah, because that plus constant is really important when you're doing an indefinite integral. It wraps it up and gives you an accuracy because when you take the derivative, that constant goes away. Okay, so there we go. Number 13, I had to do integration of parts twice. Looks like 19, same thing. So like we'll see in a little bit that e to the x kind of does the same thing as sines and cosines, where it just keeps going back and forth. So you can start spotting like when to do integration by parts really easily because you'll get this function that kind of doesn't go anywhere. And then you'll get this other function that will reduce every time you do a derivative. So 19 is going to be really easy to work with, but I got to do integration by parts twice. So it's like a little time consuming, but I don't have to put a lot of thought into it. Okay, so number 19. Excuse me. I have to do the Lie thing. There we go. And then my little integration by parts pattern. So I've got, let's see here, u dv is equal to u times v minus integral v du. Okay. And then let's see. So from Lie, there's no natural logs, there's no arc sines or arc tangents, but there is an algebraic expression, x squared. So let u be equal to x squared. dv is equal to the rest of the stuff, e to the x dx. du is equal to 2x dx. And v is going to be equal to e to the x. Okay, so now let's write this thing out. We've got x squared e to the x dx. That's equal to u times v minus v du. So that's going to be x squared e to the x minus integral e to the x times 2x dx. And let's make that look a little bit nicer. I'm going to move the 2x out to the front and then have e to the x after that. Okay, so if you've done integration by parts and it works out, that means that the integral has become easier. And yeah, from x squared e to the x to 2x e to the x, that's quite a bit easier. But I do have to use integration by parts again because, that 2x, I'm going to have to reduce it down to get e to the x all by itself. So I do Lie again, no natural logs, no arc sines, no arc tangents. but I do have an algebraic expression 2x, so let u be equal to 2x. That means that dv is equal to the rest of the stuff. And then du is going to be equal to 2 dx, and v is going to be equal to e to the x. All right, so now I just keep writing. So let's see what we've got here. It's going to be x squared e to the x. That's going to be the same, minus, and then I do my integral. Now, this is an important thing to notice. Notice that I've got this negative here. In the previous problem, when I had to do it twice, I had a plus in front of this integral. So I just kind of like put all the stuff in, you know, like all this stuff was okay because of this plus sign. But since I have a minus sign right here, it's going to be distributing on this whole integral, okay? So what I'm going to do is put a parentheses up here and then do my integral, because 2x e to the x uses this uv v minus v du. So u times v, which is 2x e to the x, and then minus v du. So that's going to be e to the x times 2 dx. And I'll move the 2 kind of in front of the ex. There we go. So now this is why that step's important. When I distribute this negative in, I've got the signs everywhere. Like if I had only put the negative on the uv, the negative also wouldn't have, you know, not canceled this negative, but multiplied out of this negative to make a positive. So be very careful when you have a negative in front of this integral. Just like remember that it's going to be distributing. So just to kind of like remind yourself, put parentheses up if you have to do integration by parts twice and you don't get rid of the negative in front of the second integral, you know, to start off. Anyways, so if I distribute that negative in there, I get negative 2x e to the x, and then a negative times a negative is going to be a positive, so plus integral 2 e to the x dx. And this is going to be super easy from here on out, right? Like that's a really, really easy antiderivative, because antiderivative 2 e to the x is just 2 e to the x plus my constant. There we go. Now I'm all done. All right, so that was number 19. Let's see what else we got. Integration by parts. Where are you? Here we go. X e to the x. Okay, so this one's a lot easier than the previous one. So obviously, yeah, Lie. So algebraic expression is going to come first. So we do that one first. Let's see. So then my pattern, u dv, uv minus v du. So I'm going to let the u part is going to be x, and then the dv part is going to be equal to e to the x dx. So du is equal to dx, v is equal to e to the x. So when I write out my pattern, x e to the x, it's going to be equal to u times v, so x times e to the x, minus integral of v to u. So that's going to be e to the x dx. And this is a really easy antiderivative, just e to the x. So this becomes x e to the x, and then minus e to the x, and then plus my constant. And that's it for this one. Okay, next up, number 36. Let me get some water real quick. So hold on a second. Sorry, my throat was getting a little dry there. Okay. So for number 36, it's an improper integral. I'm going to save all of the improper integrals for like a video like in the future, so like a different one. But I will do the integration by parts on this. So I'm going to solve for the integral for number 36. I'm just going to stop short of actually doing the improper integral part. So there's this method that you can use for number 36 and then also for number 40, where you use a u substitution, then you use an integration by parts. And so the idea is this. You start off with noticing that it is a u sub, because, you know, the u sub, it's a composition. You take the derivative of the inside function, and that usually shows up on the outside part, like somewhere multiplied in. That's a u sub. But sometimes when you do a u sub, you're still left with an integral where you have to use integration by parts. And that's where you just use both methods. The tricky part about that is this. When you use a u substitution, right, you use the letter u. Well, where else does u show up? Well, it shows up in integration by parts. So if you've got to use both a u sub and also integration by parts, sometimes it gets a little tricky to keep track of where all of your U's are and all that stuff. But I just want you to know one thing. In a U substitution, you can use any letter that you want. You don't have to use U every time. You can call it like a W substitution or a H substitution or something silly like that. It doesn't matter. And same thing with integration by parts. We just use U and V because it's convenient, but like, you don't have to use the letters U and V for integration by parts. You could use like two of your other favorite letters, like A and B or something like that. That really doesn't matter. Okay. So to kind of like combat that, when I know I have to do a U substitution and integration by parts, sometimes like I can't see it initially. So like I'll start with my U substitution, but in my integration by parts, I might sometimes change the U, and the DU to a W instead and a DW. Okay. That's just like, so I don't mix up the letters that I'm using, the variables that I'm using, so I don't confuse myself. Cause like, that's like one place where the calculus can get a little confusing. It's just if you confuse yourself on it. But otherwise, I think it's pretty straightforward. Anyways, so let's do this integral. I'm going to forget about the bounds on this for now, and then just attack those later. So I'm just going to pretend this is an indefinite integral and work on this. Okay, so here's how I do it. I got my integral x natural log of x squared dx. Okay, so first I notice that this is a u sub because I've got a function inside of a function, x squared inside of natural log of x. And then if I let u equal x squared, I've got the derivative of this. Well, give or take a multiplier on the outside. So I've got an x and a dx. I'm missing a 2. So if I put a 2 up there, I've got to put a 1/2 out front there. So that gives me everything that I need, the 2x and the dx, and then the x squared is in there. So this is a u sub. So I'm going to rewrite this as a u sub. So I've got a 1/2 integral. And then 2x dx just becomes a du. And then the rest of it is just going to be the natural log of u. Now, here's a problem because, and this is why you have to use integration by parts. There is an antiderivative of natural log of x, okay? But it's uncommonly used to memorize, so like if you want to memorize it, you can, if you want to look up the pattern. But other than that, like, since we only know how to take the derivative of natural log, in our little memorized techniques, you've got to use something else. And the only other thing that you can use is integration by parts. So this is where we got to kind of like go out on a limb here with our Lie stuff, right? Because the first L in Lie is log natural log. And we do have a natural log of u here. So I'm going to do my integration by parts, and I'm going to let the u part be equal to natural log of u. Now, I say u part in there, because I've been using this, like u dv is equal to uv minus integral v du. But since I'm already using a u here, right, I'm just going to change that to a w. Okay, and it doesn't really matter what letter you use, but just to keep everything kind of the same, I'll just do that, okay? All right, so for my w function, right, I'm going to let that be equal to the natural log. And then my dv is going to be equal to the rest of it. Now, what's the rest of it? So if I'm using up the natural log here, the only other stuff is du. And that's actually like perfectly acceptable. That's good. So now dw is going to be equal to the derivative of natural log of u, which is 1/u du. And then dv, if I take the antiderivative of it of du, is just going to be a u. So then that means that with integration by parts, this integral becomes the following. It's going to be 1/2. And then let's see here. So it's going to be u times v. So this thing times this thing. So like that. Okay. So it's going to be natural log of u times u minus integral of v dw. So that's going to be u times 1/u du. See, that's actually going to be really nice because what happens to that u and that 1/u? They just multiply to become just 1. So now the antiderivative for this part's like really, really easy. So we've got 1/2 the natural log of u, and let me move that other u out front. There we go. Minus, and then antiderivative of 1 is just, the variable, so it's going to be u, then plus my constant. Okay, now I'm going to substitute back in. So remember that u was x squared. So I'll plug in the x squared. So I've got 1/2 x squared natural log of, and that should be absolute. No, not absolute value. X squared, there we go, minus x squared plus c. There we go. So there's our antiderivative for this one, doing a u substitution and then an integration by parts. And this antiderivative is what I'm going to use for improper integrals. So, maybe like just keep it off to the side somewhere. Come back to this problem a little bit later when we do improper integrals in a separate video. Okay, next up, I've got, let's see here, it looks like number 40. Yeah, so number 40. And it's going to be the same thing. It's going to be a u substitution, and then it's going to be an integration by parts right after that. Okay, so let's see why that's the case. And let me erase all this stuff so I get a little bit of room to write. Okay, so let's see here. Well, first we would see if it's a u sub, because we go through our memorized rules. Then u sub, this would be a u sub. So we see a function inside of a function x squared. So 2x to the third cosine of x squared dx. Okay, so I let u be equal to x squared just to test the waters. And du is going to be equal to 2x dx. So I can replace that x squared with a u. And then I need 2x and a dx. Well, I've got x to the third there, and I can split x to the third apart to be x squared and x multiplied together. So this gives me the 2x and the dx that I need to replace with a du. So let's change that to a du now. There we go. But I still have that x squared left over. And, you might be confused. You're like, oh, how do I get rid of that? Well, remember that x squared is u. So you can just replace that part with a u. And now now we can do this u substitution because we replaced all of the x variable with this u. So we substituted out the x stuff for u stuff. Okay, but here's the problem. After the u substitution, yes, this is a lot easier to work with, but it's still an integration by parts problem. And it's one that you've seen before. You saw it as x times the cosine of x dx. So this is going to require you to use integration by parts. So we'll use that same pattern that we did before with the w's and all that stuff. So w dv is equal to w times v minus integral of v dw. And in this case, if we use Lie on this, the algebraic expression u is going to be the one that we're going to use equal to w. So w equals u. dw is equal to du, and then our dv is going to be equal to the other stuff, so cosine of u du, and v is going to be equal to sine of u. All right, so now when we use integration by parts, here's what we end up with. So it's going to be this times this times and then minus that times that, so it'll be u times the sine of u minus the integral of v dw, so that's going to be sine of u and then du. Excuse me. All right. So now we just go ahead and go through our last antiderivative right here, negative sine. So what do we have here? We have u times the sine of u. And then the antiderivative of a negative sign is a positive cosine. So we have positive cosine of u and then plus c, our constant. And then we're going to plug back in our u expression, and u was x squared. So, we just plug in that. So x squared sine of x squared plus cosine of x squared plus c, plus c, our constant. Okay, there we go. That's another problem done. And then let's see, do we have any more integration by parts? Yeah, 2 more. Oh, and we do have another u substitution with integration by parts. So that'd be nice. Okay, so 46. This one's going to be much more straightforward integration by parts. So if you use the Lie thing, we have a natural log right there. So u is equal to natural log of x dv is going to be equal to the rest of it, which would be x dx. Okay, and then du is going to be 1 over x dx. Antiderivative of x is 1/2 x squared. All right, and then writing out the pattern. So the original integral x natural log of x dx is equal to u times v minus v du. So that's going to be natural log of x times 1/2 x squared minus v du, which is going to be 1/2 x squared, and then times 1 over x dx. Okay, and this is really nice because if you notice, the x squared and the 1 over x like kind of reduce a bit. So x squared over x just gives me a single x left over. So this is like a really easy antiderivative now. Okay, continuing on, we got, and let me clean this up a little bit. I'm going to move the 1/2 x squared to the front. So 1/2 x squared, natural log of x, minus, and then antiderivative of x is going to be 1/2 x squared, and then plus my constant. And I can just leave it like that, and that'd be my answer. So there's number 46. 48, let's see. I might need a little bit more space. Okay, so I'll just erase all this stuff real quick. Okay, so this is going to be another u sub to integration by parts, and here's why. You notice it's a u sub first because the inside function, if I take its derivative, I can get that stuff on the outside. So let's do that. So we've got 3x natural log of x squared dx, and then like if I let u equal x squared, du is going to be equal to 2x dx. And sure enough, I've got an x and a dx here. I'm just missing a 2. So what I'm going to do is I'm going to move that 3 out front. And then I'm going to give this a 2. And then to make sure that I don't change anything, I'm also going to divide by 2. So I'll leave that 3/2 maybe out front there. Okay, so now I've got my 2x and dx. And I've got my little x squared there. So this becomes a u. And 2x dx becomes a du. Okay, but this is kind of like a little bit of a tough antiderivative. If you've memorized it, you can just do it straight up, but otherwise you got to use integration by parts, and that's what I'm going to use. Okay, so natural log of u du, and then that 3/2 out front. I can't forget about that 3/2 also. So just make sure that you remember that multiplies out every time. Let me think. It might be kind of like a little bit sloppy or a little bit challenging to keep track of that 3/2. So what I'm going to do is like move that in front here. Okay, just like keep it as part of this whole thing. And the reason I would do that is because otherwise I've got to multiply that 3/2 in every single time that, like we'll distribute it in at the very end for everything. Okay, so if I keep the 3/2 on there though, this isn't going to change anything really in the long run. It'll make it easier though. All right, so let's go ahead and work through it. So the thing that we're going to take the derivative of is going to be the w. So here's how our pattern is going to look. W dv equals wv minus integral v dw. So our w is going to be, let's see here, the natural log. So from Liate, it's going to be the natural log of u. That means the dv is going to be the rest of the stuff. So it's going to be the 3/2 du on there. Okay, so dw is going to be equal to 1 over u du. And then v is going to be equal to antiderivative of 3/2 du is 3/2 u. All right, so then we write up our little pattern here. So make a little nose there. So there we go. So it's going to be natural log of u times 3/2 u minus integral of the v part, 3/2 u times dw, which is 1 over u du. And yeah, you see immediately that this thing is going to get a lot easier, right? Because that u and that 1 over u, that's just going to make it 1 overall. So, that's pretty much gone. And then our antiderivative is super easy from here on out. It's going to be, let's clean up this first part here. Let's make it 3/2 u, natural log of u. and then minus the antiderivative of 3/2 du would be 3/2 u, and then plus our constant c. Okay, and then let's go ahead and plug back in. So u is x squared, so we just replace all that stuff, 3/2 u, which is x squared, times the natural log of u, which is x squared, minus 3/2 u x squared, plus our constant c. Okay, so there's all of it. And that's all the integration by parts problems on this worksheet. You know, they're not terribly difficult once you like get the pattern down. But you know, just practice them. Okay, that's it for this video. I hope it was helpful for you. If not, go get some help from your calc teacher. They're more than willing to help you out. All right, so that's about it. See you in the next video. Bye-bye.